Okay, this video we're gonna look at making Lewis dot structures AP style. So in regular chemistry, we had some pretty basic ones, but we're gonna start with some basic ones. I'm gonna give you the rules for making Lewis dot structures and walk you through a couple of examples. So in any structure, what you wanna do is you wanna start with counting valence electrons. For every molecule, you gotta count them and write them out. For ions, you want to add additional electrons for each negative charge, or you want to subtract for a positive charge. So I'm going to start off with molecule PF3. So on PF3, we have P, which is in this column right here on the periodic table. Remember, the columns go 1, 2, 3, 4, 5, 6, 7, 8. So P is in the 5th column. Ignore the middle columns, and it has 5 valence electrons. F is in the 7th column, 7 valence electrons. So I have P has 5 plus 3 times 7, because there's 3 Fs. So that is 21 plus 5, 26 electrons. Next, you're going to put the least electronegative atom in the middle. We're going to draw single bonds connecting the outer atoms to the middle. H will never go in the middle, so you don't have to worry about the electronegativity of that. So if I look at the periodic table, F is the most electronegative element, and everything going away from that is less electronegative. So P is the least electronegative. F will be the most electronegative. So I put P in the middle. And I connect 3 Fs like this. That is my initial structure. Okay. Next, we are going to count. So just gonna go with this next 2 rules here. So the next 2 rules are, we're going to count 2 electrons per single bond, add additional electrons on the outer atoms while counting to the target. So let's do that one first. So 2 per bond, my target is 26. So I go 2, 4, 6. And then I'm going to keep adding additional electrons to the outer atoms. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so I have 24. I still am too short of the target. So if you are at that, you can say, well, if there's extra electrons, then I put them on the central atom. Sometimes this can exceed 8. So I have 2 extra electrons that I need to use. I'm going to put them on the central atom, and that's how you get this structure. Once you have all the electrons done, you can do what's called an octet rule check. So step 5 is you're going to check the octet of each atom. So you can see here, step 5 is check each atom for octet, except for H. H should only have 2. 8 electrons are on each thing. Exceptions are BE or B. So I'll show you that in a minute, but let's do our octet first. So by doing this, I take the P, I can draw a circle around it, and I can make sure I have 8 electrons in the circle. So I have 2, 4, 6, 8, so that's an octet. If I draw an F circle, I go 2, 4, 6, 8, and you do that around everything, you can see that I have 8 around everything here. Now, what if I have something such as BEF2? So BEF2 is an example of an exception because I have 2. Okay, so I have 2 for the BE, 7 again for the Fs. So 2 plus 2 times 7, 14 plus 2 is 16. So BE, F, F, 2, 4, 6, 8, 10, 12, 14, 16. In this case, I checked my octets, and it is actually okay. So BE is an example of an electron deficient model where BE can have just 2 bonds, and that's fine. Same with boron. Boron can have 3 bonds. One common example is B with an F here, and an F here, and an F here. And these are both okay structures because those 2 atoms can be electron deficient. But what if I have something like SF4? Okay, so SF4, if I do these rules for SF4, I'm going to go ahead and follow this. This is got 6 outer electrons plus 7 times 4. 28 plus 6 is 34. So if I'm drawing SF4, that's going to have S with F, 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 and F. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I am too short of my target. And rule number, which one is it? Rule number 4 says, well, if there's extra electrons, put them in the central atom. Sometimes this can exceed 8. Well, I do have 2 extra electrons. That means I'm going to put 2 extra electrons on the S, and that is okay. So this is an expanded octet, and I have 2, 4, 6, 8, 10 on the S, and that's fine. As long as it has 8, it's got more than 8 in this case, and that is okay. So some of our dot structures may look like that. That is quite all right. Okay, now, what if we have something such as, so what if I have a molecule like this? I have CH2O. CH2O is, if I have 4 outer electrons plus 1 times 2, because H has 1, plus O has 6, so 10 plus 2 is 12 electrons. Following my rules, I got least electronegative, so C is going to go in the middle. I'm going to put an H on each side, and put an O here, okay? So now I count 2, 4, 6. I have a bunch of electrons I got to never put outside electrons on H. So 2, 4, 6, 8, 10, 12. Now if I do my octet rule check, if I look at this here, this only has 2, 4, 6 electrons. And I need to have 8. So now I have to have an additional rule because I got to have an octet here. So this is where rule 6 comes into play. So rule 6 says, if an atom does not have a complete octet, then you got to move a pair of electrons from an outside atom to form a multiple bond between that atom and the central atom. We're going to continue to do so until the octet rule is satisfied, and we're also going to make sure that we check for least variation in formal charge. So this is a lot of stuff here. I'm going to show you each part. So I got to move, it says I got to take a pair of outer electrons and move it down so I can form a multiple bonds. In this case, the O has extra electrons. I'm going to take this pair of electrons, I'm just going to move this down and make this a double bond. So now my circle has 2, 4, 6, 8 electrons. My octet rule is satisfied, and this is a double bonded C and O here, okay? If I do something like HCN is got 1 plus 4 plus 5. So that equals 10 electrons. So I put C in the middle, H, N, 2, 4, 6, 8, 10 electrons. I do my circle and I can see that I do not have an octet here. So I need to make an octet. I gotta make some multiple bonds. I cannot do any double bonds between H, so I'm gonna take this, move this to the middle. Still not 8, so I gotta do another one, and I can actually have a triple bond here. So ideally you would have an eraser and erase these from your test, your AP test, but here I just crossed them off. So single bond, triple bond, this is an okay structure. Octet rule is satisfied. What if I have something like CO2? So CO2 is probably one you should memorize, but we're going to go through and show you with formal charges. So C has 4 plus 2 times 6, 12 plus 4, 16. So C in the middle, O, O, and then I have 2, 4, 6, 8, 10, 12, 14, 16. Okay, I need to get my octet rule. And so here's two possibilities. I can go move this here and get a double bond here. I can also, now I'm at the point where I can go, well, what if I can move one of these in here and make this a double bond on both sides. Or I could go C single bond O and triple bond O. Let's put the dots over here, okay? So the question is, which structure is preferred? This one or this one? And the way you answer that is by looking at something called formal charge. So formal charge, you calculate formal charge on each atom. Basically, you take the valence electrons, the number of valence electrons for that atom, minus the bonds, minus dots, okay? And that's the number. So if I look at this one up here, oxygen has 6 valence electrons. So I'm going to take 6 minus bonds, 2 bonds, 2, minus 1, 2, 3, 4 dots, equals 0. So this is a formal charge of 0. This one is also 0 because it's the exact same thing, just mirror image. C has 4 valence electrons, minus 1, 2, 3, 4 bonds. There's no dots on it, so that's also 0. So this is 0. Okay, so this is all formal charge of 0. Here, this one is an O with a 6 minus 1, 2, 3 bonds, minus 1, 2 dots equals plus 1. So this is a plus 1 formal charge. Over here, I have 6 minus 1 minus 1, 2, 3, 4, 5, 6 dots equals negative 1 formal charge. And this is also 0. So by formal charge variation, we want the least variation in formal charge. Ideally, you want all zeros as formal charge. So this structure is preferred because we want to have all zeros as formal charges. Okay, so the next molecule we're going to look at is CO3 2-. This is a ion, so it's got a 2 here. So C has 4 plus O has 6 times 3 plus 2 electrons for that because I have 2 negative charges. So 18 plus 2 is 20 plus 4, 24 electrons. So once again, C in the middle, O, O, O. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And I don't have an octet. And so the question now becomes, well, I have 3 opportunities for the double bond to form. What do I do? And the answer is you have to do all of them. So this is rule 7. Rule 7 says if an extra bond can come from different outside atoms, then you gotta draw resonance structures to show the possible variations. So I'm gonna show you how to do resonance structures. I'm gonna first take this one here. So I'm gonna take this and move this in like this. This is one possible variation. Because it's got 2 minus, I'm gonna put brackets around the whole thing and put a 2 negative charge out here. This tells me that the ion whole thing has a 2 negative charge. Now, because this structure can also have a double bond here or a double bond here, I gotta draw a double arrow like this. And then now I'm gonna make the other 2 structures. So I have C, double bond O here, like that. This is gonna be the single bond. Okay, so this is 2 minus also. And then I could draw another, I'm running out of space on my paper, so I'm gonna draw it down like this. You get the idea. C, double bond O, single bond, single bond. Okay, so this is the resonance structure. It does not mean that the bond actually flips back and forth. It means that all the bonds are actually somewhere in between the lengths of a single bond and a double bond. It's about 2/3 single bond, 1/3 double bond character, but that's how you do resonance structures. So in a nutshell, that is how you do Lewis dot structures AP style.